All right, I think we're recording now. Okay, so in section 6.2, we're going to be talking about multiplying polynomials. Section 6.1, you're going to learn all about how to classify polynomials, how to talk about polynomials, what the, basically like the building block stuff. And then you're going to learn how to add and subtract. I've already talked about that. Section 6.2 is how to multiply with polynomials. Now, I'll tell you right now, multiplying polynomials, the more organized you are, the more organized you are and the more clean you are with your work, the better off you will be. I promise you. People whose work tend to be messy and scattered don't do very well with multiplying, and honestly for dividing as well. So I am going to encourage you to stay organized. Okay? Now, what do you intuitively think you should do with this problem? And that's exactly right. All we're really going to be doing today is doing the distributive property. That's all multiplying polynomials really is. It's the distributive property, just over and over and over again. So let's multiply in. 4y squared. Well, what's y squared times y squared? Now, be careful. Did we add exponents or did we multiply them? You add them. When you multiply bases, you add exponents. Just as a reminder, if you've got like y to the third times y to the fourth, that's y to the seventh, right? When you multiply like bases, you add exponents up top. So I know this is kind of a tricky one because it's adding 2 plus 2 is the same thing as multiplying 2 times 2. But be careful there. 4y to the fourth plus 12y squared. Pretty simple, right?
Good thing I kept my work order.
Really, right? That one was rough if you didn't. So now we multiply in. What if we've got multiple variables and more than just 2 pieces that we want to distribute in? Well, the process remains the same. You take this 3cd squared and you distribute it in 3 times. So I'm going to take 3cd squared times 4c squared d. So what do we do with that? Well, we just multiply the numbers together. C times c to the first times c to the second would be c to the third. D to the second times d to the first would be d to the third. (3c d squared times negative 6cd would be negative 18 c to the second d to the third. 3cd squared times 14cd squared would be 42 c squared d to the fourth.
That door locked.
Doesn't lock.
I'm sorry.
Questions about that? Now, let me ask you something here. This is not in your guided notes, and you don't even have to write this down, but I wanted to ask you something. What would you do here? You'd FOIL this, right? And sometimes people think foiling is some magic thing that happens when you've got a 2-term times a 2-term. You guys understand that it's just the distributive property, right?
Yeah.
First, outer, inner, last is really just first, outer, inner, last. You're just doing the distributive property. It's just a fun, catchy way to remember to do each part, right? You're just doing the distributive property. So this is kind of like foiling, but there's no fun acronym to remind you how to do it. You're just going to distribute. You're going to distribute with the A, and then you're going to distribute with the negative 3. So let's distribute with the A first off. Bring A into all parts of the trinomial on the right. Trinomial meaning 3 terms. Trinomial on the right side. A times 2 is a 2A. A times negative 5A is a negative 5A squared. A times A squared is an A to the third. And now we bring in the negative 3. Negative 3 times 2 is a negative 6. Negative 3 times negative 5a is a plus 15a. Negative 3 times a squared is a negative 3a squared. And now we combine. Now, I like to put things in what's called standard form. In section 6.1 video, you're going to learn that standard form is just basically decreasing in order from greatest to least in terms of the degree, power. A to the third minus 8a squared, just combining like terms, plus 17a minus 6. Questions on that? Okay, so let's keep it going. Even with a trinomial times a trinomial, a 3-term times a 3-term, you're still just doing the distributive property. This is where we need to stay organized. This is where you really need to be careful. Don't drop a sign. Don't forget a coefficient. Watch your powers. X squared times x squared is x to the fourth. X squared times 5x is 5x to the third. X squared times negative 2 is a negative 2x squared. Okay, let's distribute in the negative 4x. Negative 4x times x, negative 4x to the third, negative 4x times 5x, negative 20x squared, negative 4x times negative 2, positive 8x. And now we distribute in the 1. But distributing in a 1 is just going to keep everything the same. X squared, 5x minus 2. And now we combine like terms. The biggest power that I see is an x to the fourth, and there's no more of those. I like to cross them off as I go. I see a 5x to the third, a negative 4x to the third, to make just an x to the third. Those are gone. A negative 2x squared and a negative 20x squared and a positive 1x squared. That gets me a negative 21x squared. Those are gone. 8x and 5x make 13x. And then bring down our minus 2. All terms are accounted for. As long as you stay organized, and as long as you're careful, the process is not difficult. You're just doing the distributive property and then combining like terms. So let's work with some powers. Did I lose anybody there? Anybody still need the work for this one? Yeah.
Just on the combining like terms, why don't you combine the x to the fourth and x to the third?
If I was multiplying, I could combine them. But because they're not the same variable raised to the same power, I cannot add or subtract them. Any other questions on this one? Let's take some powers. Now, people, everybody watch on the board real quick, please. Please don't do this. Please, please, please. Please don't do this. You cannot distribute the power like that. That does not work. Those things are not equivalent. I wish it was. Honestly, that would be very easy to do. That would be really nice. Because I'll tell you what, this problem is pretty difficult. I don't want to say pretty difficult. I mean, it's kind of labor intensive, but it's not too bad. I'm still just doing the distributive property. But please, please, please do not just distribute the power. I could distribute that power if there was no adding or subtracting on the inside. That plus right there in between the a and the 2b is stopping me from distributing power. If this was a times 2b, then I could distribute the power because it's all multiplication. But because it's addition or subtraction, no good. All right, so what do we have to do then? Well, I have to take a plus 2b times a plus 2b times a plus 2b. And now it kind of sinks in that this is going to be a little bit more work than just distributing in the power. All right, so I like to start at the end for some reason. I like my bigger polynomial to be on the right side. So I'm going to multiply those two together. And I have to FOIL those together. Now I can change the order and it's not going to change the outcome, right? That's the commutative property. of multiplication. I can change the order and it will not change the outcome. So I'm going to take, I'll just bring down this a plus 2b. A times A times 2b, 2b times A, 2b times 2b. Please try to keep things in alphabetical order. When there's a term that has A's and B's and C's, keep them in alphabetical order. That's going to help you. Like you wouldn't want to call this third term 2BA. Right? 2BA, you may not see that it would combine with this other 2AB. Right? You might get stuck. A squared plus 4AB plus 4B squared. And now we have to distribute in. This problem becomes example C, where we got a binomial, 2 term, times a trinomial, 3 term. A times A squared, A times 4AB, A times 4B squared. 2B times A, 2B times A squared. 2B times 4AB, 2B times 4B squared. And now we combine like terms. That gets me an a to the third. I like to go in descending order when there's more than just one term, more than one variable. I go in descending order of the first variable alphabetically. So I'll go with the a's. So I'll find my next 4a squared, or my next a squared. So it looks like it's an a squared b. That was gone. A squared b and an a squared b. So it looks like 6a squared b. And then I've got 4ab squared, 8ab squared. And then I've got a plus 8b to the third. Again, stay organized. Stay clean with your work. Let's try one more though. X plus 4 to the fourth. Yeah.
6 in front of the a squared, like the second part, right?
This right here?
Yeah.
Yep, 6a squared b.
It wasn't a b.
No, I know my 6's and my b's.
No, it's okay.
I blame my elementary school teachers. You know, I used to write 6's like this. Like, I started from the inside of the curl, and I would go like that.
Why?
Oh, that's interesting.
Isn't that weird?
I don't know that I've
You've entered a lot of.
So I've tried to really emphasize the shorter curl like that to make it look different from my b's. But
Write it going from the top.
write it like that.
You don't?
No, I don't.
You were for elementary.
Start from
writing
the-
6s like
You start from the inside too?
Yeah.
You write it like that? Just looks like a spiral.
It looks like that.
You can't leave a spiral space that like makes it like a
I know.
curly cue.
I know. All right, x plus 4 to the fourth. Now, let me tell you guys something. There will be something like this on the quiz on Friday. Do you guys understand the implications of if you just say x to the fourth plus 4 to the fourth, like how much you're cutting off? Like this problem is going to take a lot of work. Probably going to be like 5-6 points on the quiz, maybe more. I can't give any partial credit if you just do that, because none of that is right. Partial credit is
What if we simplify that to 16?
no.
Okay. Making sure.
But take a look at what we have to do. I mean,
Is it one for each side though?
what do you mean?
Like, can't you just do like the right side and we know that's what the left side will be?
Yeah. See, this is what's cool about this one is when you have an even power like that, you can set them up as doubles. Because aren't those two going to come out to be the same thing? So really, I mean, that just cuts away on one piece of foiling. X squared plus 8x plus 16. Quick math. I'm going to start doing that, folks. I'm going to start just combining like terms right away. Like I don't want to write out the plus 4x plus 4x. Shortcut to that is if you've got a binomial squared, you can just square the first, square the last, and double the product. Okay, that's a quick way to FOIL something with two terms squared. Square the first, square the last. That's where I get the x squared and the 16. And then I double the product. 4 times x is 4x, double it, 8x. Okay, and now we have to take a trinomial times a trinomial, which we've done that already. That's example D. You just got to be careful. X to the fourth, 8x to the third, 16x squared, 8x to the third, 64x, 128x, oh, that's right. 16x squared. Oh, 16 times 8 again, that's 128. 256.
This is 64x squared in green.
Yeah, I always drop powers like that. I'm bad at that. That's where I am careless. Whenever I multiply with x's, I drop powers all the time. If I'm checking my own work, that's where I check first, because I'm bad.
I love how there's all the sixes on the board now.
I know, it's like,
I'm very.
who's the devil here? All right, here we go. X to the fourth, 8 makes 16. X to the thirds, 16, 64, and 16 make 96. X squareds. 128 and 128 make our 256. And then plus 256.
That was fun.
Yeah, that was a good time. I had fun. Now, I'll tell you this. Whenever you have a power, whenever you have a two-term, which is called a binomial, raised to a power, there's a shortcut. Some of you guys might not think this is a really shortcut, but there is a shortcut. And it uses this thing called Pascal's triangle. You guys ever hear of Pascal's triangle? Let me first start off by telling you how to construct Pascal's triangle. Okay. Now, Pascal's triangle is not something that Pascal made up. Right? He just saw patterns and wrote them down, and that's how that's he got the money for it.
Did he give you something else too?
The what? No, you're thinking of Pavlov.
No.
Oh my gosh.
They're both Russian.
No, Pascal's French.
Same thing. They're both in Africa, okay?
Yeah, his first name is Blaise.
Why did he
Yeah.
spell it like that? It'd be so much cooler if it was in
Yeah.
I know, but he's French, so it's like Blaise. Now, just don't tell.
Don't tell the French people.
Okay, India is totally. That's more Italian. My French and Italian. All right. Now, to construct Pascal's triangle, you start with a triangle of ones, and then each subsequent row starts and ends with a 1, and all the middle numbers are a sum of the ones above it. So 1 plus 1 is 2. Okay. Start the next row with a 1, end it with a 1. 2 and 1 make 3. And then you keep going. And you may be thinking, this seems silly. Why how is this going to help us at all?
Trying. Now it's like an awesome triangle. How many times do you do it?
And this process could go on infinitely, right? What Pascal noticed is that there is, did I do something wrong? What's
I
up?
had a question.
Yeah, what's up?
I was gonna say, so like on the test, we have to be able to solve normally and Pascal's triangle.
Yeah, I'll ask for work using Pascal's triangle. So Pascal was just basically like, I see patterns in there, and he wrote them down. Here's just a little bit of patterns that we see. The Pascal's triangle task cards kind of delves deeper a little bit more into it. But first off, we see the ones, the big ones along the outside. We see this natural number set, which is also actually the row number. The row number. So, which implies that this is actually the 0 row. Yeah, that's row 0. And you'll see why here in a second. This is row 2. Oh, sorry, excuse me. This is row 1, this is row 2, this is row 3, row 4, and so on. Okay. We also see 1, 3, 6, 10, 15, 21. Up by 2, 3, 4, 5, 6, 7. Right, do you see that? Look at the pattern there. Go up by 2, up by 3, up by 4, up by 6, you know? There's something here. 3, 6, 10. Oh, that's what it is. Now you're going up by these numbers. If you look at the diagonal here, you're actually increasing an amount of this. There are all sorts of different patterns, including the sum. Look at the sum of each row. 1, 2, 4, 8, 16, 32. What do you notice about the sum? Doubling, which actually means it's 2 to the nth power, where n is the row number. 2 to the 0, 2 to the second, 2 to the, 2 to the 0, 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth, and so on. Okay, so there's a lot of different patterns. And now, Pascal didn't invent this thing. He just wrote it down, right? There's actually, there's been things found in ancient Chinese writings that have this triangle. They just don't find all the patterns that, ancient Chinese don't end up finding all the patterns that Pascal found. Now, one thing that is very, 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 very useful is called binomial expansion. Okay? And we use Pascal's triangle to expand binomials. What do I mean by expand binomials? When you multiply them all out, that's expanding binomials. Right? We expanded x plus 4. Right? And we got that big long polynomial. We can use Pascal's triangle to find the coefficients. Take, for example, here. This is a plus b to the 0, right? What's anything raised to the 0? A plus b to the first is itself 1a plus 1b. A plus b to the second power. And now you'll just have to trust me. A plus b to the third. A plus b to the fourth. What do you notice about all the coefficients? It's the same as Pascal's triangle. Okay? All of the coefficients end up being the numbers from that row of Pascal's triangle. So this will actually help us in expanding binomials without having to multiply it all out. Let me show you how. Let's take x plus 2 to the fourth power. What row of Pascal's triangle do we need? The fourth row. Row 4. That's the 0 row. This is the first row. Third. Fourth. I know it looks like the 5th row down, but again, the row number is, well, the one that's second number is 4. Right? That's the row number. So this is what we need. Those are going to be the coefficients of each term. So here's the setup. Here's the setup. I'm going to start off each term with the coefficients. And now what we do is we take the first term out of the binomial. The first term out of the binomial is x. We're going to give it the largest power. And then we decrease in size each subsequent term until it's no longer there. The second term of the binomial is 2. We start off at the end, giving it the highest power. And now we go up the ladder, decreasing the power as we go until it's no longer there. You take your first term, you decrease in order of power. You take your second term, you're kind of increasing in power, but you want to think of it as starting from the end and moving back upward. And now at this point, you just simplify. X to the 4th plus, okay, I've got a 4 and a 2 to make a total of 8 in the second term. 2 squared is a 4. 6 times 4 is 24. 2 to the 3rd is an 8 times 4, 32. And then 2 to the 4th is 32. No, it's 16. I'm sorry, it's 16. Oh, my power's 2. That's my answer. I didn't FOIL anything out. Now, could I have, I find this quick because I can do that in my head pretty quick. You guys may need some time to really kind of get comfortable with it. I want to do one of the harder ones because we're going a little bit short on time. Let's do example C. 6m minus 8. It's a little bit more difficult when you have numbers and variables. I'm going to jump to example C. Oh, you know what? Shoot. I'm sorry. Let's do D. Because honestly, raised to the 3rd power, just multiply it out. If I've got something raised to the 5th power, think about how difficult this would be to actually just go through like brute force and multiply it out. Let's try to do it with Pascal's triangle. There's the 5th, row 5 of Pascal's triangle. 6 terms total. 1, 5, 10, 10, 5, 1. I like to space everything out a lot, just in case I need room. I start with my first term, and I give it the highest power. 3a raised to the 5th. And I keep descending. You should run out just before the end. Then you take your negative b, make it the highest power at the end, and work your way forward, decreasing in power by 1. Until it's no longer there. And there's the setup. And now we simplify. Okay, I've got 3a to the 5th. I can distribute the power here. 3 to the 5th, don't know that one offhand. 81, 243, I think. I better look at that. 3 to the 5th. Yeah, 243.
I don't know offhand.
It was easier than I thought. 243, a to the 5th. And now for this second term, I'm writing a minus in there because look, this negative b is going to change my sign. And then I've got 5 times 3 to the 4th. 405. A to the 4th, b. Now, is the negative going to factor in here for my next term? No, because it's squared. The negative will cancel. So this is going to be 3 to the third, which is 27 times 10 is 270. A to the third b squared. The negative is going to play a role in this next term because it's raised to the third power. Odd powers leave negatives. Minus 3 squared is 9 times 10 is 90. A squared b to the third. Negative b to the fourth, raising it to the fourth power, eliminates the negative. 3 times 5 is 15. Negative b to the fifth. There it is. So again, if you would like to take your guided notes, you can pick them up as you leave. I have to put more guided notes up there. Everything is accessible online with the exception of the actual guided notes paper. In fact, if you wanted to take the notes by hand, you could do that too.
Oh, I hated that. If I was the guy that invented that, I feel so bad.
Christian, you like that?
Yeah.
I knew that if I didn't like that.
Thank you.
I still want to actually like get on track before I walk on.
Oh, I gotta stop the recording. Oops. Whoops.